So in this video, we are going to continue using matrices to solve our systems of equations. We have to make sure we know how to enter them in. We're going to convert our equation into an augmented matrix, and then we're going to be plugging that in, letting the calculator do the reduced row echelon form. So it basically does elimination for you, and it's going to spit out this matrix. And then once it spits that out, we have to make sure that we understand that those are your x's, your y's, and your z's. And there's our answer. All right, so these are going to be special cases on these last two. So we just want to make sure we know what it looks like and how we deal with it, because there's definitely going to be a difference between the result you get here and the result you get here. Okay, so we got to understand your special cases are going to be no solution and infinite solution. So we got to make sure we understand the difference between them. So first thing is, on this thing, we're going to write it in an augmented matrix, and so that is making sure that everything is all lined up, which it is. And so we're going to have 1, -3, 8, and then -2, 6, 3. And this is 2 rows by 3 columns. I need to know that because of the calculator. So I'm going to go matrix. We're going to edit, and we're going to turn this into 2 rows by 3 columns. So that is a 1, -3, 8, and then -2, 6, 3. Okay, so we have all of that. And now we're going to let the calculator do its thing. So our matrix is ready to go. We're going to go into the matrix world, and we're going to go up just because it's quicker to get to the row reduced echelon form. So that's just basically elimination. And we're going to do matrix A. All right, so our matrix that we get out of this so it definitely looks different than the prior two. The prior two, you had this diagonal of 1s and nothing else around it except for the last row. So the last row are kind of the values, and then these diagonals represented your x, y's, and z's. So when you don't get that, that means you have a special case. But you got to figure out what kind of a special case. So when you have 2 zeros here where you're basically, it stopped the diagonal, but you do have a value here. This represents no solution. Okay, so for 2 variables, 2 equations, these lines would be parallel to each other and they don't cross. So that's what a no solution looks like on this. If you were to get an infinite solution, you would have a 0 here and you'd have a 0. So you'd have a whole row of zeros, and you're going to see that on the next one. But when you get a 3 by 3, a 3 equation, 3 variable, your infinite solution means it's a little bit trickier. You have to account for the fact that you have this line of infinite solutions, and so you're going to have to create a variable appropriately, because as one variable changes, it causes them all to change a certain way. So we'll do that in this next one. But if you get a row of 0 except for the last value, that's a no solution. All right, so on this one, we're going to do the same thing. We're going to make it into an augmented matrix. All the x's, y's, and z's all line up. So we got 1, 1, 1, 1, 1, 2, 3, 4, 4, 5, 6, 7. Okay, so there's our augmented matrix. We're going to plug it into the calculator. So matrix, this is a 3 by 4. All right, so 3 by 4. We have a 1, 1, 1, 1, and then a 1, 2, 3, 4, and a 4, 5, 6, 7. All right, so we'll quit out of that. We'll let the calculator do its thing. So we're going to do our reduced row echelon form for matrix A. That's what we used. All right, and then let it do its thing. So it's the last row. And because we don't have a 0 right there too, that's kind of another indicator. So 0, 1, 2, 3, 0, 0, 0, 0. All right, so here is our infinite solution. So this is what tells us we have an infinite solution. So what we're going to do is, we do have infinite solutions. However, what we're going to do is we're going to lock z. Okay, so everything that we're about to create in this coordinate is going to be all in terms of z. Okay, so here's what we got going on. So if we actually turn this back into an equation, this is your x column, this is your y column, this is your z column. So you have an x minus z equals -2. So x minus z equals -2. So we are going to solve for x and make everything in terms of z. So if we bump our z over, we'd have x would equal a positive z minus 2. And then if you did the same thing on this equation, this is y plus 2z equals 3. So if you subtract your 2z over, y is going to equal -2z plus 3. And so here's what your answer looks like. Your x value is actually z minus 2. Your y value is -2z plus 3, and your z value is just your z value. So as z changes, your infinite solutions aren't just random infinite solutions. They're all dependent upon each other. So as z changes, it changes these values to a very specific combination. So if you have a 1 here, you'd have a certain value here and a certain value here. If you had a 2 here, you'd have a different value and a different value. So they're very, very specific, and we've made it all dependent upon z. Z ends up being the easiest one to ever do. So it's pretty much always you're going to do this in terms of z, because you're going to have an x all by itself, you're going to have a y all by itself. So the other two values are going to be z's, so that you can get them by themselves. So you can move them over and isolate the x and the y, and then rewrite your equation. So that is your final answer, is your infinite solutions in terms of z. So as z changes, it causes the others to change. So those are your two different scenarios for your no solution. If you had a 3-equation, 3-variable, you would be looking for a 0, 0, 0, 1 or some other number, and then that would tell you it's actually a no solution. So you wouldn't have to do this, you would just flat out say no solution. All right, so that was using matrices to solve a system of equations. 2 variables, 2 equations, 3 variables, 3 equations, but using matrices.